Hi everyone, it's Mr. Patron, and in this video we're going to take a look at creating ionic formulas through the use of polyatomic ion. So we just went through your polyatomic ion POGL activity in breakout rooms in class, and this video, like I said, is just going to kind of recap some of that information and go through how to get the formulas for some of these well-known compounds. So I'm just going to share my screen to this guided note set here. So make sure that you're following along with this, whether you've printed it out or you're typing along in Google or you're just writing your own notes in a notebook, whatever works for you, whatever you've used in the past for this kind of stuff. So here we're looking at ionic formulas with polyatomic ions. So after your exploration of polyatomic ions, and that happened with the POGL activity with your groups, this video, like I said, is going to go over some definitions and how to approach these compounds that contain polyatomic ions. So to start, I'm going to give you a definition. So polyatomic ions are groups of atoms that come together to form a charge. That come together to form a charge. Sorry, this was a little slanted. So once again, polyatomic ions, prefix poly means many, atomic refers to atoms, and ion, we should know, is a charged version of an atom. So a polyatomic ion is a charged version of an atom, but it consists of multiple atoms grouped together as opposed to just one. Monatomic ions are just the solo ions, such as like sodium with a +1 charge. It's just one sodium atom that has this charge. Whereas polyatomic ions consist of several atoms grouped together. Now, as we mentioned, several compounds contain these polyatomic ions, and I'm going to go over the formulas and how to go from this. So you're going to look at table E in your reference tables. So table E is on page 2 of the reference tables. It's called selected polyatomic ions. So it's going to be right here. So you'll have access to it through this, but you should also have your own copy on you. If you have a printed version, that'd be great. So by using table E, we can easily write out ionic formulas with these polyatomic ions based on their name. So table E, like I said, shown to the right here. So if you're given the name of a compound, there's just a few steps that we're going to follow to get you the proper formula. So we're going to go over the example calcium phosphate. Calcium phosphate. So calcium is a metal, it's in group 2. Phosphate is one of these polyatomic ions in here. So I'm just going to clear this so I can scroll down. So the first step we're going to take is we're going to identify the cation and anion by their name and their formula, and this is going to include their charge. So in typical ionic naming structure, so this is an ionic compound, so it's going to follow the same protocols that we learned when we focused on just regular metals and nonmetals. The first name, the first word here is the cation, is the positively charged. So the cation is going to be calcium, and the formula for this is just going to be Ca plus 2. Calcium is a group 2 metal. It's an alkaline earth metal. It has 2 valence electrons, so it wants to lose those 2 in order to look like a noble gas. That's why it is a +2 charge. The anion here is phosphate. So phosphate is one of these polyatomic ions. Typically, you can recognize them by these common endings. So something that says "ite" or "ate." So you'll see like a lot of like carbonate, oxalate, chlorite, chlorate, chromate. So that ending is pretty indicative of it being a polyatomic ion. So if it looks a little different from a normal element, check this chart just to check, just to double check. You never know. may mix a couple of them up. So we see like nitrite, very similar to nitride, which is just the regular ionic version of nitrogen. So just be very careful with these here. So, and then just some more information about these. Most of the polyatomic ions are negatively charged, so they are anions. And phosphate is one of those examples. So phosphate is right here. It might be a little tough to see, but it is the formula of it is PO4, and it has a -3 charge. So 1 phosphorus, 4 oxygens, and then they're all grouped together and they produce this -3 charge. There are some positively charged ones, some cations, so be on the lookout for those. They're not all negatively charged, and they're actually in this top left area here. These are all of the positively charged ones. We have hydronium, mercury 1, and ammonium. Ammonium is the one that is most commonly seen, so just keep an eye out for these as well. Okay, so we know our cation is calcium, it has a +2 charge, and we know our anion is phosphate, and that has a -3 charge. Okay, so once again, I'm just going to have to clear this to scroll down, but I will rewrite this information. Okay, so the second step is to combine these two ions to create the base of the compound. So this is going to include our charges, but leave out the subscripts. Those subscripts are the numbers on the bottom. So we're not worrying about those right now. So just to remind ourselves, our cation was calcium +2, and our anion was phosphate, PO4, with a -3 charge. This is from our table E. Okay, so we're going to combine this to create the base of this formula. So like in the other ionic formulas that we've looked at, the metal comes first, the cation itself comes first, so calcium, and we're going to keep the +2 charge up here. And the anion, so phosphate, comes next with its -3. So this is going to be some iteration of CaPO4. So we're going to follow the same process that we followed when we're creating these ionic formulas with a regular ionic compound or a binary ionic compound. So like with calcium chloride, Ca is +2, chloride is -1. There are a couple steps that we took to determine the true formula. Very similar process is going to happen here. I'm just going to clear this. Okay. So our main goal here is to determine the number of each ion that is needed in order to obtain a neutral charge, so a total charge of 0. Now, there's 2 ways we can do this. Like I said, very similar to how we did it with the the binary ionic compounds. So we could do the adding up charges method or the crisscross method. And I'm going to go through both strategies here. So the adding up charges method is the one where we kind of list out the ions themselves and kind of just total up their charges until we reach a balance of 0. So if we take 1 calcium +2, and then a phosphate, -3, +2, and -3 is going to give us a total charge of -1. So we're not ready yet. So we have -1, we need more positive to balance that out. So we'll throw another calcium on, Ca +2. Now we have 4 in the positive side, and then 3 on the negative side. Now we have more positive than negative. So we'll add on another phosphate because that has our negative charge. PO4, -3. Now our total charges, we have 4 on the positive, so +2 and +2 gives us +4, and then 6 on the negative. So -3 and -3 gives us a -6. Still need some more positive now, so we're going to add 1 more calcium, Ca +2. Now, if we look at our total positive, we have +2, +2, +2. That's a total of +6. And then on our negative side, -3 and -3 gives us a total of -6. So these values are balanced. So what this says is that the crystal formula for this ionic compound consists of 3 calcium ions for every 2 phosphate ions. So much like we did with other compounds, we would write those using subscripts. I'm going to go over that in just a bit. I want to go through this crisscross method first, and you'll see there's a reason why I'm going over that afterwards. But just to restate, we're going to have 3 calciums, 3 of these, and 2 of these. Now, I'll show you how this works with the crisscross method. So once again, the crisscross method is kind of like our shortcut version. So we take our ion and their charges, so Ca plus 2, and then we have PO4, -2. I'm sorry, -2, -3. So you may recall what we did here. Take the charges that are in the top and then drag them to the bottom of the other ion. So the 2 belongs to the phosphate, the PO4, and the 3 now goes to the calcium. So this is going to leave us with calcium 3 times. So like we said before, 3 calcium ions. And then we have 2 phosphate ions. So PO4, 2. Now, if you look at this, there's something that's not really too clear here. And there's something that we can fix to make this a little bit more clear. So from my eyes, it looks like we have 3 calcium ions, one phosphorus atom, and then 42 oxygen. Now, we know that that's probably not the case. If we look at the adding up charges method that we did, we have, yes, 3 calciums, 1, 2, 3, but we have 2 phosphorus atoms here, and then 4 and 8 oxygen atoms. So there's something we can do to fix this, and it's in this note down here. So it says, and I'm just going to actually erase this circle I made because I realize it's blocking part of this. So it says, if you have a subscript surrounding a polyatomic ion, you will put the ion in parentheses. This demonstrates how the atoms stay together as one ion, and it also eliminates the confusion of it looking like we have 42 oxygens here. So to fix this, we are going to put parentheses around the phosphate ion, this PO4, and this 2 just goes after that group. So our final answer here, our final written formula is going to be Ca3 parentheses PO4 2. So once again, we have our 3 calciums from here. And then the fact that we put these in parentheses, much like in math class, we grouped up the phosphate ion, which is composed of 1 phosphorus and 4 oxygens, but we needed 2 of them. So this parentheses indicates that there's 2 of these whole sets. All right. So this is how you determine the formula of a compound containing polyatomic ions from the name. So the rest of this assignment consists of some practice questions. So I'm just going to clear this and scroll through to show you. So there are some practice questions here where you are going to look at the name and then use whichever process you like, adding up the charges or using the crisscross method, to determine the proper formula. Once you determine the proper formula here, there is a Google Sheet that you have been assigned. And if you enter all these answers correctly, you should see an image pop up in the Google Sheet as you work through it. I won't tell you what it is. Hopefully you will find out. Along with that, this page here is asking you to determine the names from the formulas. So it's a very straightforward process, very similar to how we determine the names from formulas of regular ionic compounds. So just use your table E to appropriately identify the correct polyatomic ion and use that in the naming structure. Okay, so if you have any specific questions, message your teacher, and good luck. All right, have a good one.